Today our speaker is Valentina Lozza, a colleague from LEAP, from the neutrinos group, as you know. So Valentina has done her PhD at the University of Trieste in Italy, working within the CAST experiment at CERN for the search of solar axions. Then she started to work in the field of neutrino physics in 2010 as a postdoc at the Technical University of Dresden, joining the SNO Plus collaboration. In 2017, Valentina moved to LEAP Lisbon as an FCT researcher and kept working in SNO Plus, where she has and had many coordination roles. She has been the coordinator of the radioactive background group since 2011, was the analysis coordinator of the partial field physics between 2019 and 2022, and became the physics analysis co-coordinator of the collaboration in 2021. So she specialized in low energy radioactive backgrounds, in the search for neutrinoless double beta decays, and in measurements of solar neutrinos and reactor anti-neutrinos. So today she will talk about the current status and also the prospects of the liquid scintillator phase of SNO Plus.
Thank you. Can you hear me? Fine. So, okay. So yeah, thank you, Ruth. Sophia presented at the beginning of this year in April the results of the water phase of SNO Plus. So to conclude the year, I will present the next part, which is the scintillator phase of SNO Plus. So first of all, for the few of you that might not know, SNO Plus is a large detector located in Canada, to be precise, at Sudbury. Here you have the surface building where we have some of the clean rooms and most of the offices, but the real laboratory is underground, is about 2 kilometers underground, is the deepest underground laboratory in terms of the muon flux reduction. Compares GPing is as an horizontal access, while SNO Lab is a vertical access, so you really need to go in a mine and then work in the mine underground. The detector is a multi-purpose neutrino experiment. It means that we have as major goal the search for the neutrinoless orbital decay, but we can do also many other physics topics. Here you have a view of our detector, as made of an acrylic vessel of 6-meter radius, 5-centimeter thickness. And the light that is produced here by particle interacting with the different media are seen by about 9,400 photomultiplier tubes that are placed on this stainless steel structure that is called PISA, PMT support structure. And everything here, so between the acrylic vessel, the photomultiplier tubes, and the cavity where the detector sits, is filled with ultra pure water that acts as a shield against various radiation. The detector here is filled with 3 different media. So we had at the beginning ultra pure water, about 905 tons. This phase went until 2019, what Sophia presented the main result at the beginning of the year. Then we started to remove the water and replace it with liquid scintillator. Currently, the detector is completely filled with 780 tons, more or less, of high purity liquid scintillator. To this scintillator, we add a fluor and then a secondary wavelength shifter in order to shift the wavelength of the photons that are produced by particles interacting in the media to where the PMTs are more efficient. And then the next phase that will start next year is that we will load 3.9 tons of tellurium inside the detector. Tellurium is among the candidate isotopes to search for the neutrinoless orbital decay, and has been the isotope selected by SNO Plus. And this will be the largest mass used for the search for neutrinoless, largest tellurium mass search for the search of the neutrinoless orbital decay. As I said, we have several background reduction layers, one of which is the ultra pure water that fills the cavity and the space between the acrylic vessel and the photomultiplier tubes is used to shield from the neutrons that are produced in the rock or the gamma rays from the PMTs themselves. Then on the top of this one, this is called the neck, is where all the tubes for filling the detector and so on run. On the top of this, we have nitrogen blanket. The detector cannot be sealed. It needs to breathe. Otherwise, we have problem with pressure, and the pressure on the ground is changing and so on. So we have so-called cover gas blankets. So it's a volume of bags filled with nitrogen that avoids radon to enter. So there is a slight overpressure inside that avoids radon to enter inside the detector. You know that mines usually have a high level of radon compared to surface. SNO lab, we have about 130 becquerel per cubic meter of radon, and this makes a reduction of a factor 10 to the 4, 10 to the 5 compared to what we have inside the detector. And then everything, so the walls of the cavity are covered with a plastic that also reduces the radon ingress in the water. In addition to that, we have material purification that happens through various purification plants that we have. Third purification plants are underground in order to avoid material reactivation from interaction of cosmic rays on surface. Some of the purification plants are on surface because some of the material are less sensitive to that. Among the purification plants underground, we have the one from water. This is in common to the entire SNO lab, is used by other experiments that are SNO lab as well. And then we have 3 purification plants that are exclusive of SNO plus. One is for the liquid scintillator that we have recently used to fill the detector. And then we have 2 plants that are used for the components of the tellurium cocktail. In order to make tellurium to connect with the liquid scintillator, we need to add some components. It's not just tellurium. So we have one that is purification of the diol. Diol is a material similar to liquid scintillator. And then one for the tellurium itself. This is actually the most important one to be underground because the activation of tellurium by neutron and protons on surface can create, even if a small amount, but can create isotopes that can be a problem for us. So having it underground as an additional shield against this reactivation. We have also the possibility to, once the detector is filled with liquid, to recirculate it. This is also used when we need to add material. So we extract or from the top or from the bottom, add the material, and then recirculate the entire detector to have a full mixing. And we also do constant assays in order to check the optics of the detector, of the liquid scintillator, to be sure that what we are adding is not creating any issues. And to act promptly if not. So before adding anything, we extract part of it, we do an assay of its optical purity, and if everything is okay, we continue. Otherwise, we stop and we search for the problem. So as I said, primary goal is the neutrinoless orbital decay, but we can also do solar neutrinos, reactor, and geo anti-neutrinos, be watching for supernova and search for rare decays. Obviously, the tellurium search can be done only in the tellurium phase, but the other measurements can be done in all the phases, besides geoneutrino that could have not been done during the water phase because the threshold was too low and we were not sensitive to the geoneutrino. They have too low energy to be seen in the water phase. So before going to the scintillator phase, a bit of recap of what we had before, so a journey of SNO plus. In 2017, between 2017 and 2019, we had the so-called water phase. It was divided in 2 parts because we did some detector operation in between. Among this operation was the addition of that cover gas blanket that I said at the beginning, which helped to reduce a lot the background inside the detector. So in this phase, SNO Plus operated as a water Cherenkov detector, pure water Cherenkov detector. So we had the Cherenkov rig and reconstruction of this one. We had different outcomes. One is the search setting limits on the nucleon decay mode into invisible channel, like for instance, neutron decay into 3 neutrinos and so on. So we had the best limits. This is our new measurement. These are the existing limits. Some are actually, the number 6 here is us in the first phase. So in the second phase here, we beat ourselves. So we had the best limit for these decay modes. And then we are doing solar neutrino measurement, in particular boron 8, which is above the threshold. And actually you can see here the effect of the addition of this cover gas blanket. This was the result we obtained in the first phase of SNO+. This is the solar angle, and these are the number of events. So boron 8 neutrinos have a direction that points to the sun. So you have the cosine theta sun 1 for solar neutrino. All other events are instead random direction with respect to the sun. So they made a flat background here. And you can see this background is around 20 counts for 115 days, right? Here we increase the days and the counts are much less. This is the effect of this cover gas blanket that we put on the top of the detector that help to reduce the major background in this energy range here, that is 515 MeV, which are mainly the tail of the radon daughters. The fact that we reduce a lot the background allows to reduce the threshold for doing this measurement. So we are currently running and preparing a paper with a threshold of 3.5 MeV for the measurement of solar neutrinos. And the result of the first phase is an agreement with what SNO obtained, so for boron 8 solar neutrinos. It's our first measurement of SNO+ in water. Then this is what Sophia already presented, so if you want to go back to her talk, you have all the details about this, or can ask directly to Sophia. But we search for anti-neutrinos. Anti-neutrinos, we look for those through the inverse beta decay. So you have the antineutrino interacting with the proton, the positron, the Cherenkov ring from this one. Then it produces a neutron, right? And the neutron scatters proton and so on, and then is captured by a proton emitting the characteristic 2.2 MeV gammas. Generally, this process was not seen by pure water Cherenkov detectors because the threshold is 3.3, 3.5 MeV. What was used was detector enriched with gadolinium or other material that have a high capture cross-section for neutrons and shift the energy of the gammas emitted to high value, 8 MeV, 9 MeV, 6 MeV. But SNO+ didn't do that. We had a pure water Cherenkov detector, and we managed to lower our threshold, energy threshold, to be sensitive to this 2.2 MeV. And we had an efficiency for triggering of a neutron of about 50% at the center of the detector. This is the best that is obtained with a pure water Cherenkov detector. And we went over this, and we actually made the first measurement of reactor antineutrinos using a pure water Cherenkov detector. The two major reactors for SNO+ are two Canadian reactors at two different, so there are three at two different baselines. So we have a flux that is smaller than Camland, but the fact that we have two distinctive baselines, it helps us, and we have characteristic feature in the energy spectrum that I will show in a bit. This measurement was published. Again, Sophia said everything about it. It was a peer editor choice, and so on. So this is the signal that the prompt signal, so the neutron, the antineutrino interacting with the protons and producing the positron. You can see the backgrounds are very low. We have very good agreement within Monte Carlo and the data. The other point that we obtain, and this is important for all the next phases during the water phase, is a measurement of external backgrounds. What we mean by external backgrounds? We mean everything that is not the liquid inside the vessel. So the vessel itself, the system of ropes to hang the vessel, the water outside, the PMTs, everyththing is considered external background for us. And there are mainly gammas from the natural radioactivity. So even if we select material that are as pure as possible, you still have uranium and thorium in them. And you have gammas that are produced by the uranium and thorium decays that can reach our target material right inside the vessel. This is what we call the external backgrounds. The advantage of doing this measurement during the water phase is that we can use directionality, so this U.R, to select boxes where these backgrounds are dominant and can separate the various components. In the scintillator phase, we lose directionality, or most of the directionality, because light is emitting isotropically. So we don't know what is what. But during the water phase, we can actually separate what comes from the photomultiplier tubes. They have characteristic directionality, what comes from the water, what comes from from the vessel, and so on. So we measure all these components, we compare to Monte Carlo in various energy ranges and regions, and then we obtain the so-called fraction of nominal. Fraction of nominal, if it's 1, it means that the value that we measure corresponds to what were our expectation, where our expectation comes from ex situ measurement, which means sampling of a small amount of the material, for example, with germanium detectors or other techniques, or from measurement done directly by the previous SNO experiment. Smaller than 1, it means that, great, we actually have background levels that are smaller of what ex situ measurement gave. This is normally the case because ex situ measurement give an upper limit. Sometimes the purity is so good that with germanium detector we cannot measure that, so we can say it is smaller than. And then if it's larger than 1, it means that it's slightly worse of what were our expectation. So in general, it's good. And what actually it means, this value, it means that when we are doing the projection of these backgrounds, so if we consider that the ropes and external water and so on have a value that is that fraction multiplied by our target, and we calculate the projection in the region of interest for the neutrinoless orbital decay study, then this is a factor of 2 reduction of what if we use just the ex situ measurement. So it's actually very nice. So coming then to the scintillator phase, which is what this talk should be about, we start to fill the detector in 2019. We started to remove the water from the bottom and add the scintillator on the top. Scintillator has a density that is smaller than the one of water, is about 0.85 gram per cubic centimeter. Water is 1, more or less. So you can see here the scintillator is on the top. It makes this nice interface between water and scintillator. The water is below. This scintillator is linear alkyl benzene plus, as I said, the fluor to shift the wavelength, has been developed by SNO+, and SNO+ is the first detector going from Cherenkov detector to scintillator detector. The beauty of LAB is that it allows isotopic loading. It's important because we want to load tellurium in there for the next phases. Unfortunately, while we were filling the detector, pandemic hit, and the COVID pandemic hit, and then we had to stop. The mine was closed, we cannot go underground, we can do nothing. The detector was practically, so the access to the detector was 0 between April and October 2020. And we were with the detector half filled. So we were half of our job. We had scintillator on the top, water on the bottom, more or less divided in half. The PPO was also 1/4 of the final concentration, so 0.6 instead of the 2 grams per liter. So this is the light yield that we had, so the emitted photons per MeV of energy that we had. This was our final goal. We were about 80% of that one in that period. But actually it was very nice because even if this was unpredicted situation, and we had the complication of having an interface here between 2 different materials that have different indices of refraction and so on, the detector was very stable. So we could actually do nice physics measurement out of it. So we had these 90 days of gold physics data that we could use. We obtained the first solar neutrino measurement of SNO+ with scintillator, which is a big deal for us. We measure boronate neutrinos, so we didn't discover anything new, but we had a measurement that is compatible with what we measured during the water phase. Sure, it's statistically limited. We had only this 90 days, but we had 90 days coming for free. And we could actually check that SNO+ is working nicely, that the backgrounds were what we were expecting or even below. And we could do nice physics measurement. The boronate neutrino, here you have the spectrum. Actually, this analysis has been done by Anna Sofia, our previous PhD student. The major background is the thallium 2A that is coming from the thorium chain. This photomultiplier eats more or less the number of photomultipliers that sees a signal above threshold. 1,500 is more or less 5 MeV. So above 5 MeV, we are practically background free, and we can do a measurement of the boronate neutrinos. This is more or less the same threshold that we had in water. We also prepare for the double beta decay phase during the so-called target out measurement. So the beauty of SNO Plus is that we can measure the backgrounds before we are adding the tellurium. Sure, not the tellurium related backgrounds, but everything that is before that. Also, we are doing the so-called target out. It means that we are measuring the backgrounds in the region of interest for the tellurium studies. We can measure the background using the region above and below in energy, but it is also important to check that where we are expecting the zero new signal, there is nothing unexpected. So we are doing this check. Sure, this was statistically limited. Again, we had only here a reduced set, 70 days of physics data, but we could check that the data are actually matching our prediction. So we are expecting 8 events and we measure 2. Moreover, this background is higher of what we will expect in the tellurium phase because we have some components that won't be present during the tellurium phase. One is obviously the water, because with full tellurium, the internal water won't be there anymore. And the other is this so-called PFA tube. It was a tube that was added to the detector to extract the water from the bottom in order to fill with scintillator. This tube has been removed now. So these two major background components that are actually here won't be there when we do the tellurium phase. So this is actually important proof that all the other backgrounds, the ones that will be there when we are doing tellurium, are at our expectation. And yeah, we see 2 events, expected date. So it's again statistically limited, but the detector works and nothing unusual is in the ROI. Another important result that we obtained during this phase, plus using a full scintillator phase, we restarted the scintillator field operation in October 2020 when we could access the mine again. And then we started to fill the scintillator. And in April 2021, the detector was completely full with scintillator. What was still missing was the final concentration of PPO. So we still have a reduced PPO concentration, but it's actually good because we could do a measurement of directionality. So as I said before, so Cherenkov detector have direction, right? So you have Cherenkov ring and you can reconstruct the direction of the particle. Scintillator detector usually have isotropic light. They still have a fraction of Cherenkov photon, but is much reduced with respect to the scintillator photons. So what you have is that you don't see directionality. You don't see direction of the particle. Light is isotropic, so all the PNPs are heat. You don't have a nice Cherenkov ring form. But we could actually try to look at the Cherenkov photons that arrive first and make this. So this is the corrected time for the arrival of the photons at the photomultipliers. So we can use the first window here between -5 and 15 nanoseconds, which is the signature of the Cherenkov photons, and report to the angle between the direction of the reconstructed the photon and direction of the particle, and we can see an excess. Around 0.6 is what we expect from the index of refraction. This is for 6 MeV electrons. So when we apply this to data and boronate neutrinos above 5-6 MeV, again, the same plot as we had in water, right? Cosine theta sun, so the direction of the sun. We actually have this, using the prompt part of the time signal, we have this peak at the cosine theta sun, similar to what we had in water. So beside this is a scintillator detector, the fact that we had a reduced concentration of the PPO, so a reduced amount of scintillation light produced, we could use the part of the Cherenkov photon to reconstruct the direction of each event. This is different of each boronate event. This is different of what has been done by other experiments like Borexino, which what they used to do was to look for the direction of the event, but in a statistical way, so not event by event. It's also true that Borexino was able to make this measurement for very low energy neutrinos. So we did this for boronate neutrinos. Borexino did for beryllium-7 and SNO neutrinos, so other neutrinos are produced in the sun that have lower energy. So the extraction of directionality is more complicated for that. In any case, the event-by-event direction reconstruction was, for boron 8 neutrinos, was the first time that was done in a liquid scintillator detector. So finally, in April 2022, the detector was full of LAB with the final PPO concentration. So this is the light yield. Before we were here, and now we are here. So SNO+ started to, this is the so-called scintillator phase. So SNO+ started to run as a full scintillator detector. And so what we did now was to, of course, measure the purity. We did this in the partial field phase, but we want to be sure that the same purity that was obtained in partial field phase remain in the full field phase, so when we complete the field of the detector, and also with the final PPO concentration, right? That it's not that the addition of more fluor increase the background level of our experiment. So what we did is to track the uranium, and we do the same for the thorium using the so-called BIPO coincidences. So in the uranium chain, at a certain point, you end up with the bismuth-214, which beta-gamma decays to polonium-214. And polonium-214 decays alpha with an half-life of 164 microseconds. So we can use the coincidence between these two events in space and time to try to track them. So what we do first is to check the window of the polonium event. Alpha have a Q value of 7.8 MeV, but in scintillator they are quenched. This means that the corresponding equivalent electron energy is more or less a factor of 10. So a 7 or 8 MeV alpha is about 0.8, 0.9 MeV electron equivalent energy. So the energy that we actually is coming out from the detector. So we check this polonium, then we define the energy window for the preceding event, the bismuth-214, and we check the time difference between the two and the position difference. So the time difference is a nice exponential decay with the half-life in agreement with the one of the alpha decay, so the polonium-214, which means that we have identified the correct pairs of events. And the position difference is also this characteristic distribution with a mean around 20 centimeter-ish, 20, 30. Events that have no correlation between each other tends to be more or less everywhere in the space. So the delta R distribution, the position difference between the two, tends to increase with the distance. So the fact that this peaks, this is more or less the mean path of the gammas, like that, it means is another check that we have identified the correct events. So using this, we can then obtain, knowing the detector efficiencies and so on, the gram per gram of uranium and extract the uranium concentration. So you can see here, initially we have a decay. This decay has an half-life of 3.8 days. This is radon. Every time you have field operation in a scintillator detector, this has been seen by Borexino and Kamland as well, you introduce a bit of radon because of the part of the operation, because the plant that loads the scintillator is not 100% sealed, so you can have radon entering. This is the start of our scintillator phase, which is marked by the end of the filling operation. So we had a bit of radon in the detector, which is decaying away. This is not unexpected, this is normal. Actually, it's a good tracking thing. It has a lot of radon at the beginning. We can check that all our cuts works, that we can see how radon moves in the detector and so on. But what is important then is that is the constant part here. And this is 10 to the minus 17 gram per gram, which is below the requirement that we have for the neutrinoless orbital decay phase. We do the similar game for the thorium. Here, the coincidence is the BIPO 212. The time window that we use is much shorter than the one for the uranium chain, because this half-life is just 0.3 microsecond compared to the 160 of the other one. But nevertheless, we obtain also here, we don't have the radon decay because there is no radon in this part of the chain, or there is a radon but has very short half-life. And the concentration for thorium is also 10 to the minus 17 gram per gram, which is expected, uranium and thorium concentration are expected to be similar in scintillator detector. And again, this is also below the requirement of more than a factor of 10 of what were the requirements for the double beta decay phase. So the detector works nicely, everything is good. So backgrounds are okay, so we can do physics. And the physics that we are doing, since we don't have tellurium in there yet, is reactor anti-neutrinos and solar neutrinos mainly, and supernova. We are watching for supernova. We didn't have a supernova yet, so we are just watching for those. For the reactor anti-neutrinos, why we are doing this measurement? Because there is a tension between the experiment that have measured delta m square 1, 2. Kamland at a measurement 7.5, the solar neutrino experiment has a measure of 4.8, 10 to the minus 5 eV square. So you can see this solar, Kamland. So this is the combined result. So another reactor anti-neutrino oscillation measurement would have to clarify the tension or confirm the tension. So this is why this is where SNO plus enters into the game, right? So we are trying to do a reactor anti-neutrino measurement as fast as we can. So again, also in a scintillator, we are detecting antineutrinos using the inverse beta decay reaction, same reaction as in water, antineutrino, proton, positron, neutron, delayed gamma. But here the game is much easier because the threshold of scintillator detector is few tenths of keV, 70 keV-ish for SNO plus. So we don't have the issue anymore of detecting the 2.2 MeV gamma because it's difficult to see it. We clearly see it because it's very above our threshold. So this is the expectation. This is the energy of the prompt energy reconstruction. This is for an unoscillated reactor antineutrino, and this is for reactor antineutrino oscillation based on the two values of the delta m square 2, 1. Okay, so Kamland and solar. You can see that we have characteristic features in both cases. And this is what we want to use to extract a delta m square values for SNO plus. Obviously, there is a background as well. So this is a delay coincidence analysis. Usually it's less sensitive to backgrounds because, well, you can use the delay coincidence. So all the backgrounds that are stable are not an issue. However, there are some signals that mimic what we are searching. And these signals are, for instance, the so-called alpha N events. Alpha N reactions are practically alpha particles. The main source is polonium-210. Scintillator detector have a history of having quite some amount of this polonium-210 comes from the uranium chain and interacts with nuclei like carbon-13 and produces other nuclei, in this case the oxygen-16, and then a neutron. So more or less it's exactly the same signal, right? Neutron scatter off, you have a proton recall that mimics the positron, and then neutron capture that is exactly the same signal as the antineutrinos. So we have seen a high reduction of the polonium-210 in the full field phase with respect of what we did in partial field. This is mainly because the bulk of the polonium-210 came at the beginning of our filling operation, and then polonium-210 has an half-life of 140 days, and it started to decay. He will decay until he reaches the equilibrium with his mother, which is its mother parent, which is lead-210. So this is what comes to the end, the signal. So this is the reactor signal, and this is the background event, this alpha N events. We still have features that we can distinguish. And the other thing that we can do in order to improve our resolution, our sensitivity, is to develop a classifier that helps to separate those IBD events, inverse beta decay events, with respect to these alpha N. So these are reactor events, these are alpha N. After the development of this classifier, this is for the 0.6 gram per liter PPO partial fill, and there is a good separation between the two. And this has not been applied to the plot that I've seen before. And we are currently developing the same thing for the full fill. So work is in progress, and we hope to improve our sensitivity. The other thing we can do is a measurement of the geo antineutrinos. Well, there are few geo antineutrinos, only 25. But it's the first measurement of geo antineutrinos in North America, here, which is complementary to the measurement that has been done at Gran Sasso or Kamioka. So it is an important measurement. Even if there are few, it's extremely important because it can help to constrain the geological models. So all in all, we did a preliminary study in SNO+, using a 5.7 meter fiducial volume. This is not a fit, this is just comparing data to total Monte Carlo prediction. This is done using the Camland result. But you can see that we have features that we can distinguish, and also here, this is the geo antineutrino signal, and we can probably see those. And again, this has been done without the rejection of the alpha n events using the classifier. So it's very promising, the result that we can obtain in the antineutrino phase. Work is in progress, I cannot show the result yet. Solar neutrinos, we are also doing a measurement in this case. This is also a very preliminary, 81 days of data. Again, background free, more or less above 5 MeV. Below is the thallium-2 as expected from the thorium chain. So we are trying to extract the θ12. Again, our measurement is statistically limited for now, but we are expecting to double the statistic using more data of SNO+. So to improve this result is already quite good. So beyond the scintillator phase, this is what we get right now. So the scintillator phase has been is running, and we are preparing a lot of papers with very interesting result to come out. But then there is next, right? So there is the neutrinoless orbital decay phase. So just a quick overview about the neutrinoless orbital decay. So beta decay is forbidden, cannot happen. What happens is a double beta decay. So two is like the two simultaneous decays of two neutrons. So in the final state, you have 2 electrons and 2 antineutrinos. Only 35 isotopes do this. This has been measured, predicted by the standard model. Everything is fine. The decay scale, however, is very low, of the order of 10 to the 20 years. In addition to that, we can have the neutrinoless orbital decay. So the antineutrino is emitted in the first state if it's a Majorana neutrino, if its own antiparticle, so it flips, is absorbed as a neutrino by the neutron, and at the end you have 0 neutrinos, only the 2 electrons. This can happen only if neutrinos are Majorana particles. So if this antineutrino here can do the flip and be absorbed in the decay. The theory tells us that we can measure the half-life, and it depends on the effective Majorana neutrino mass to the square, so the inverse of the half-life to the square. It depends on the phase space factor here that goes as the Q value to the 5th power, and on the nuclear matrix elements, which are the largest theoretical uncertainties. There are various theories, various models, various differences between them, sometimes factor of 2. And the half-life, the effective Majorana neutrino mass is proportional to all the oscillation parameters and M1, M2, M3. So what experimentalist says, you have the double beta decay, and then if you have the decay without the 2 neutrinos in the final state, then the energy is shared only by the 2 electrons. So, well, it's easy. We just count the number of events that are in the Q value of the reaction. And counting by the number of these events, we can connect them to the half-life of the decay. It's not that easy, because then you have various parameters that enters here in the game. One is, okay, the efficiency of the fraction of the 0 nu that enters in this region, and then all more or less depend. This is a general formula. It can vary from experiment to experiment, but unless your experiment is background free, so you don't have background events here, so you have a linear increase with time. It depends on the square root of the mass of the material, the time, and the so-called background index and the energy resolution. You have different background indexes, what is expected by SNO+, what has been made by Gerda, what has been done by Quore. Note that Gerda and Quore are solid-state detectors, so their energy resolution here is much smaller than us, is 10th of keV, our is hundredths of keV. So it also counts when you do the B times delta E. But we still expect to beat Quarry, which was the other tellurium experiment on this. And Kamlan-Zen is the best that is done even better of what they were expecting, and they are experiment like us, a scintillator-based experiment. It's 1.3 10 to the minus 4 events per kilogram per keV per year. But what this formula tells us, this connected to the formula before, that to improve the current sensitivity of a factor of 2, you need an improvement in the experimental part of a factor of 16. So you need to have large mass, high radio purity, at good enough energy resolution in order to try to increase your sensitivity. So these experiments are difficult because it's not linear scaling. So why we are doing that? Because we want to study all these facts here, mainly to know if neutrinos are their own antiparticle, and they can help then to solve all other series of issues that we have known in physics. The results have impact across different research areas. So it's not just physics, neutrino, but it's standard model, cosmology, and so on. So the state of the art of the neutrinoless orbital decay, the three major experiments, Gerda, Quarry, and Kamlan-Zen, and then we have from this side this cosmological experiment and Katrin. This is the effective Majorana neutrino mass, and this is the lightest of the neutrino masses. So as you can see, this is the inverted ordering, mass ordering that we want to study. Kamlan-Zen, with the recent result, actually managed to touch and go beyond the inverted mass ordering. Current running is will start soon experiment are going to test the first part of the inverted mass ordering. Next generation experiment are going to go here, and only future experiment are testing the normal mass ordering, unless it is on this part here, which is yet not excluded by cosmological experiments, which are pushing in this direction. Okay. So here you have the major experiment divided in the class. SNO plus will be, Quarry is over or nearly over. SNO plus will be the only experiment running with tellurium for the future, and actually having the largest isotopic mass for the study of the neutrinoless orbital decay. Yes, it is important that we have different isotopes to test the neutrinoless orbital decay in order to test the various nuclear matrix models and so on. So again, why we are doing tellurium? Because it has high natural abundance. We don't require enrichment, which is the problem of the detector operating with xenon. Xenon 136, which is that candidate, is not as abundant. For xenon is here. They are pushing to 80 and plus % abundance, but it's just with enrichment, which is expensive. So we buy tellurium and we don't enrich. We use this 34 natural abundance. The Q value is high. The importance of having a high Q value is not only because the space factor goes as a Q value to the fifth, so then the half-life is shorter, so you have more probability of discovery, but it's also because the rate of this decay then in the region where you have the ROI is shorter, so you have less events per second. No, this is confusing two things. No, the Q value is important, it is high because it's above the natural radioactivity, while the half-life longer is that you have less events per second in the region of interest, sorry. And the major advantages of doing this search with SNO+ is that you have large detectors, large mass, rejection of uranium and thorium backgrounds, good energy resolution, and we can do this target out measurement as I've shown before, right? So we can check that we don't have anything unexpected in the region where we are expecting the zero new signal before adding the tellurium. So we know that the backgrounds are under control before adding the tellurium itself. So we started operation for filling the detector with various components that are helpful for the tellurium cocktail. We know that the light yield will decrease a bit when we add tellurium, so when we load the detector. In order to compensate for this, we boost the light yield right now so that we can then compensate for the fact that we are losing a bit when we are adding tellurium. So we added the secondary wavelength shifter to the detector. We are tracking the effect using the polonium-210 decays, that alpha decay that I've shown before. We added the BCMSB from the bottom of the detector. It started to mix. This is our equator, so the detector divided in two. This is the region where BCMSB is. This is the region where there is no BSMSB. You can see these are the PMTs. The number of PMTs that sees a signal increase of a factor 1.5 with BSMSB. Now it's completely mixed, so don't worry. The detector is fully mixed and uniform. Beginning of next year, we are testing the tellurium plant. The tellurium plant is underground, fully installed, and we are going to commission it. So we are using 200 kilograms of tellurium that is underground to actually test that the plant is working as expected. The purification factor is as expected. We will send sample for off-site ICP-MS analysis to make sure everything is okay. And then we start to add the first component of the tellurium cocktail towards the end of next year. And in 2025, we will add tellurium and start counting. So the first counting will be done with 3.9 tons of natural tellurium. This is what we are expecting. We will actually not go for 5 years, but only with 1 year with 3.9 tons and then add more tellurium, because this is the beauty of SNO+. We can add tellurium on the go. And as we add tellurium, we improve our sensitivity because we increase our mass. And hopefully we keep the backgrounds low. So that background index of before doesn't increase too much. So this is 3.9 tons of natural tellurium, 1.3 tons of tellurium 130. And these are our major background in the region where we are expecting the signal here. The fiducial volume is selected in order that an hypothetical zero new signal of 100 MeV is not dominant. So is dominant. So the external backgrounds are not dominant. And the best fiducial volume, well, is around 3.3 to 4 meter, more or less. In this region, we expect 9.5 events per year, which give the background index that I've shown before. So how we improve this background? Well, we have neutron and proton activation of the material, but we keep the material underground since 2015, and we have the tellurium purification underground. So everything is great, and this background is actually very small. In addition, we have solar neutrinos that can actually interact with tellurium and produce this nasty iodine 130, but it will also be rejected using multi-site classifiers. So the fact that we can distinguish with single state events like the neutrinoless orbital decay, and events that have more betas and gammas, so they travel more in the detector. Then we have solar neutrinos. We have to see if we can use directionality also in the tellurium phase in order to try to reject this background. If we know the direction of solar neutrinos, we can take the solar neutrinos out. And then we have uranium and thorium internal. We checked this previous to add in the tellurium. Everything is great and fine. External gammas we measure during water is actually below nominal value. So this part is cool, and they won't increase because the detector components won't change. It may be that external water sees a bit more radon, so that backgrounds might increase, but we actually have a great tuning now of the water temperature and purification. So we monitor constantly, and we see that we keep this value under control and it's not increasing. Alpha N are this background that is a background for the anti-neutrino search, but can also a background for the double beta decay phase, but is a delay coincident tagging as well as the anti-neutrinos, as we said before. So we can actually reject it. It's practically zero here. The two new, well, there is nothing that we can do about this if not improving the energy resolution of our detector. Is the only way that you improve the energy resolution, your region of interest can be smaller, the leak of the two new is smaller as well. So all in all, this is what we are expecting with 0.5% tellurium, 3 years of running. This is our sensitivity, mass. This is actually a better way to see it. This is Kamlan-Zen result, and this is us with the 0.5% loading and 3 years. This is the invert ordering. So we are also expect to touch and explore, depending on the nuclear matrix element. This is the uncertainty, right, in the nuclear matrix element. The inverse ordering region. And then we load more tellurium, and then here we explore the entire inverted ordering region independently of the nuclear matrix element, and then we load more. So our goal is 3% loading, and you can see our expectation is 10 to the 27 year and to touch the entire inverted ordering region. To go here, we need 10 to the 28 or more years which means we need a lot, much more mass. So this is beyond what SNO+ can do. So summary, SNO+ has successfully completed the scintillator phase, scintillator filling with a 2.2 grams per liter as of April 2022. Now we have started to put the components for the tellurium cocktail, right? We started with B7SB. Next year we will go with the next one. 2025 is when we are expecting to add tellurium in our detector. And then, yeah, there are many publications using this tellurium phase, this scintillator phase that are coming out. Thank you. I'm done.